cost of the breakers implementations. Okay, so I have another video here showing how does the air blast breakers works. Okay, so let me share my screen. Okay, I will change to another Chrome here. Okay, wait, yeah. Mm, mm,
We'll use a simplified illustration to look at the arc-interrupting features commonly found in air blast breakers. The main features include conductors, contacts, a blast valve, arc chutes, arcing probes, arcing rings, and arcing electrodes. The air inside the breaker head is pressurized. Compressed air has a higher dielectric strength than air at atmospheric pressure. Now, the main current path in this type of breaker is through the conductors and the contacts. Let's take a closer look at one of the contact assemblies with the contacts open. The assembly includes a set of main contacts and a set of arcing contacts. Now let's close the contacts and see how the breaker works to open the circuit and extinguish the arc that is created. When the breaker trips, the contacts begin to move apart. The main contacts separate first. Arcing does not occur because the circuit is still complete through the arcing contacts. As the contacts continue to move, the arcing contacts separate, creating an arc. The arc is quickly extinguished by a number of features that work together. Let's go back to the breaker in the closed position to see what these features are and how they work. One feature is the blast valve. When the breaker is closed, the blast valve blocks the arc chutes. As the contacts separate and arcs form, the blast valve moves, uncovering the arc chutes. When the chutes open, the pressurized air in the breaker head blasts through the arcs and through the arc chutes to atmosphere. The blast of air helps cool the arcs and at the same time forces the arcs away from the arcing contacts and toward arcing probes and arcing rings. An arcing probe and arcing ring are conductors that help carry the arc away from the contacts. As the contacts continue to separate, the distance between the contacts becomes greater than the distance between the arcing probe and arcing ring. The air blast through the arc path forces the arc off the contacts and across the probe and ring. The air blast continues to elongate the arc and forces it off the arcing ring into the arc chute to an arcing electrode. By this time, the air blast has stretched and cooled the arc enough so that it extinguishes at a current zero and the circuit is opened.
So you can see how does the air blast circuit breakers works lah. Okay, so let's move on back to our slide. Mm, mm, mana? Okay. Okay. All right. So you have watched this video, yeah? So you can tell us that the design of this air blast circuit breaker is much more complex, unlike the one I have shown you just now. It also consists of what arcing ring, arcing probes, and so on. But I hope that the animation will give you better understanding of how it works. All right, so let's move on to the next kinds of breakers here. So I will not give you breaks right now. If let's say you need, I will give you. All right. Do you want to continue the class or you want to have a break first? Seeing as it's a lots of theory right now. Are you still able to absorb? Hello? Break okay, let's have 5 minutes break lah. Okay, so I will continue the class at 5:07 lah. Okay, so 5 minutes has passed. Let's see, okay, the continued topics we have here. So this time we'll look into the other kinds of breakers we have, where right now we are using the sulfur hexafluoric gas as the insulation medium for arc preventions. Okay, so this time you will look into the animations here. The circuit breaker's tank, right, will actually fill with the FSX gas here, all right, where this FSX gas is known as the electronegative gas that has high tendency to absorb the free electron. That's how we reduce the ionized particles. So as a result, the dielectric strength of the medium, which is the FSS gas right now, can grow much more faster as comparing to the restricting voltage. So the arc able to be extinguished. All right. So for this kinds of breakers, right, it's very popular to be used in a complete range from medium voltage to higher voltage applications up to 800 kilowatts or even higher. So with this properties, right, it makes it very suitable to be applied for the metal click switch here, where inside there will be a bus bar that expected to have a high fault current through, and even for a hybrid high voltage substations. So now for this depth tank design of the circuit breakers, inside will fills with the FSX gas lah. Okay, so now let's move on here. We have a field photo showing how does the circuit breakers works as well as how it looks like. Okay, so for this FSX gas, right, not only with depth tank design, we could have lifetime design as well. So right now the switching unit is actually located inside I mean with the puffer types of insulators. So what happens if we take this up, cut in the cross section wheel, and put it like this, stand vertically? So this is what you will see inside. So you will notice that we have two components here being colors in orange. That are actually the contacts. This is the fixed contact. This is the movable contacts. So you can see, right, these two contact is mixed like a cylindrical shapes with hollow at the centers. Okay, so take note that for this movable contact, it will be in sync with the valve that control the opening for the FSX gas lah. So during the time, if we have separations of the contact, the arcing process is actually occurs here at the arcing contact tips here, right? So now this FSX gas, right, after the arc extinction, it will actually move away from this powerful cylinders design here. All right, so now let's see how it works. So we will zoom into these four figures here. All right, go to the next slide. It's showing the four stage of the operations, all right, for this FSX gas circuit breakers. So the first one here is under normal conditions with no faults at all, right? So you'll notice that this is the protective tubes. This is actually the puffer cylinders. So if you measure the pressure difference where the FSX gas is inside, right? Under normal conditions, the pressure at these protective tubes as well as the puffer cylinders, right, they're actually equivalent to each other's. So whenever there's no pressure difference, there will be no movements of the gas, right? So what happens if we go to the second stage here? So during a time, if we have faults, right? So this contact, this is actually the mobile contact. So this is the fixed, this is the mobile contacts under normal conditions that are touching with each others. So what happens if this mobile contacts start to move downwards after getting signal from the relays? So you can see right here that is how to say the arc being occurs at this particular point, the arcing tips here. All right, so under these situations, whenever the contact starts to separate, there's actually pressure difference right now. So inside this powerful cylinder, let's say the measure pressure is P1, and inside these protective tubes here is with the pressures of P2, right? So you will notice that the pressure inside is actually much more bigger as comparing to the pressure outside, which is at the protective tubes here. So whenever we have pressure difference, there will be a movement of the gas I mean the FSS gas here, right? So with such a case, you can see following these arrows here, this is where the gas flow. So whenever the gas flow, this is actually the arc, right? It will actually along the arc like this, okay? So this is actually the stage 3, all right? So you can tell, right, before these contacts are fully opens, right, actually the arc is already as eliminated. So at the stage 4 here, you can see this is the final positions of the movable contacts, and you can tell, right, the arc is actually eliminated. So that's how it works for this FSS gas. They're actually well enclosed inside. There's no discharge of SF6 gas here to the atmosphere. So the movements of the flows of the gas is actually via the pressure difference between that one at the protective tubes. Another one here is inside the puffer cylinders. Okay, so now let's see what is the advantages of using the FS6 gas circuit breakers in the next slide here. Why it is so popular to be in use. The first one here is because the arcing process, the duration is actually very short. So with such a case, the arcing energy produced will be low as well. So now the contacts of the breakers will not being damaged so soon. So the contact erosion will be much smaller. So that is the first advantages. So moving on here for the FSS gas, right, it has the excellent property in terms of high dielectric strength. So which means that it's not easily being break down and turned into ionized particles. So with such a case, because of these properties, right, so the arcing process will be shorter, so it's able to interrupt much higher fault currents values. Okay, so this is the advantages of FSX gas. So if we compare with the air-blast circuit breakers, there is no need of the compressors, right? So with such a case, whenever it's operate, we have noiseless operations. This is due to its design. It's well enclosed inside. The movements of the FSS gas is through the pressure difference inside this puffer cylinders right now. And at the same time, right, there's no discharge of the arcing byproduct to the atmosphere if we are comparing with the air-blast circuit breakers. So that's basically its advantages as well. And the last one here is actually comparing with the oil breakers. So we know that for this FS6 gas is not flammable. So we can actually eliminate the risk of having the fire hazards, right? Like the one we have for the oil breaker. So this means that FS6 gas circuit breaker can actually apply for much higher voltage applications. Right, so here are all the advantages, but it has some problems as well. So let's move on to the next slide here. So for this gas is actually very expensive, so it's make it non-economic viable. Let's say you have a limit budget for the protections purpose. And moving on here, right? So every operations of this FS6 gas circuit breakers, which means that after is interrupt the fault from the system, this gas has to be reconditioned. So in such a case, right, we need an equipment for this. So is make these systems here, I mean the SF gas breakers here, become even more expensive whenever we want to use it for protection purpose. So overall, we can say this is an expensive choice we have for the circuit breakers. And this FSS gas itself, right, is actually identified as the greenhouse gas. So if let's say if there's a breakage for the structures, which means that FSS gas might leak or discharge to the environment. So with such a case, it will be harmful for the population. Let's say it's being leaked to the atmosphere. So it actually contribute to global warming because it's considered a kind of greenhouse gas. So details at the bottom here is a little bit out of topics, right? We are trying to compare if let's say we have leaked the FS6 gas here to the atmosphere, how actually it contributes in terms of global warming. So to measure the global warming potential, right? So now which means that we want to know how much this released gas in terms of mass, means in kg or grams here, contribute to the greenhouse effect. which means that global warming. So in other words, we will use this GWP here to measure how much CO2 has been discharged to the atmosphere. Okay, so now if we comparing the carbon dioxide and the FSS gas, right? So one carbon dioxide, if let's say you release to the environment, this is with the values of ones. If we compare with FSS gas, right, in terms of GWP, it will contribute 22.2 thousands. So with such a case, right, what happens if we release 1 kg of FSS gas here to the environment? So it will be equivalent to situations whereby we have drive a car with the total mileage of 120,000 km, assuming that this car, right, every km you travel, you are releasing 185 grams of carbon dioxide. So you can see how bad would be if, let's say, if there's a leakage of FSS gas here to the environment. All right, so now that is for these kinds of breakers. So now we have the next types of breakers to be introduced to you is known as vacuum breakers right now. So the methods to eliminate the arc is by using the vacuum, of course. So the ideas behind for these kinds of breakers, right? We are trying to empty the air inside the breakers right now, so it's free from any molecules, no gas inside. So with such a case, the arc is hardly to be generated. So which means that we know that the arc is generated through the ionized atoms, right? So if we have vacuum conditions, we have lower chance for the arc generate. Let's say there is a separations of the contacts for the breakers right now. So how actually we can achieve the vacuum conditions is by maintaining the pressure in between this range for this vacuum breakers here, 10-7 to 10-5 torr, where torr is the unit for the pressures at absolute scales. You can also convert into Pascal. Okay, so now for these vacuum breakers, of course, there's a pro and cons, and it has been summarized in these tables here. Okay, so in terms of structural design, so for vacuum breakers, right, is compact, which means that smaller size and it has a longer lifespan. Okay, in addition to this, because of the vacuum's environment, the arcing energy generated will be very low as well because the arcing duration is low. With such a case, right, it able to how to say, to break any heavy currents here perfectly before the contact reach its definite open position. Why it have these amazing features here is because like this. Let's say this is a current waveform for the AC system, right? So now whenever the current reach at this 0 point here, right? So now it will actually build up the dielectric strength for the vacuum much more faster. Okay, so which means that whenever it's built up the electric strength, so at these moments of time, the fault current is already isolated since the arc has been eliminated. Okay, that's how it's able to achieve this. So it's break the fault currents before even the contacts fully opens. And moving on to go back here, right? So now we have vacuum situations. There's no gyrations of gas like FSS gas or even the compressed air, right? So now during these operations, there's no gyrations of gas. Okay. And the last advantages of using the vacuum breakers here, basically it also able to withstand the lightning surge as well. So here are all the pros of using the vacuum breakers. So how about the problems there? So the problem might be faced whenever we are implementing the vacuum breakers here. If let's say we have these situations, these tanks of the breakers have damage. So we have loss of vacuums right now. See, as the air can go inside. So we could have the air atom inside. So during the moments, if we have separations of contacts, the arc is actually there because we doesn't have the vacuum situations. And these problems, right, are unable to be repaired on site unless you replace it with the new tank here. Okay. And for this vacuum breaker itself, right, it's also not economical to be used if, let's say, we have the system voltage more than 36 kilowatts. Why? Because it's very costly for us to generate the vacuum conditions for the circuit breakers operations. So this is basically the problems we have for the vacuum breakers here. Usually we will only apply for up to medium voltage applications, all right? Only up to here, 36 kilowatt, not higher than this, okay? So yes, you thought that this is the last breakers we have, right? Sorry, we have one more. It's known as the air circuit breakers, okay? So for this air circuit breakers, right? So both of its contacts, right, is actually operating open and close, interrupting the arc under the atmospheric pressure conditions, which means that it's unlike this case here under vacuum with high pressures, or maybe like the FSS gas here, remember, is has different in terms of pressure. They actually operate under high pressure conditions. But for air circuit breakers, it happens at atmospheric pressure conditions. So how does it work to interrupt the arc rate? It's actually different as comparing to those kinds that's being introduced to you just now. So it's actually achieved by having the high resistance method, right? So we can do it in this way here. First, by intense cooling of the arc plasma. So with such a case, the voltage gradient to maintain the arc is actually become much more higher. Right, with the same voltage value, the arc is unable to be formed. The second way, again, lengthening the arc path. So increase the distance between the gap for the contacts of the breakers. That's how we increase the arc resistance. And the third way is by using the iron chute or the arc splitter. So we split the arc, the big one into smaller arc. Okay, so that is how does the A circuit breakers works. All right, so now we have a sample photos here showing the air circuit breakers. Okay, switch here, right? Inside there is a circuit breaker. So if you open up, the circuit breaker is actually located inside as a part of the switch gear. So for information, this switch gear is actually located somewhere in University Malaya lah. Okay, if you stand nearby this, right, see as the arcing is element inside, right? And actually, if you stand nearby, you feel that it's a hot, how to say, you feel the hot sensations. If let's say you stand beside this air breakers right now. Okay, so now let's move on till we have one table showing the comparisons for different types of breakers that has been introduced to you, where different types of breaker has been classified based on what is the medium we have used for the arc animation. So we have one, two, three, four kinds here for the first tables, A, oil, FSS gas, and vacuums here. So in terms of numbers of operations, okay, so obviously for oil breakers will be the lowest, its lifespans will be the lowest, followed by the air and FSS gas breaker, and the best one will be the vacuums breakers lah. The next one is in terms of soft breakability. So most of them is with good performance, only the vacuum with fair performance. The third item to be compared right now is in terms of medium. Do you need to monitor it or not for its proper operations? So for air breakers, as the arcing terminations is occurs at atmospheric pressure, you can't control it. Okay, so it's not applicable for the air breakers. How about for oil breakers? Yes, you need to manually test it whether this oil still serves as a good dielectric mediums to be used. Seeing as every arcing process, the oil will be being collected. So there's a need to monitor the oil. The third one is FSS gas here. The operation is actually automatic. So just to remember, it flows based on the pressure difference at the protective tubes as well as the puffer cylinders, right? So you doesn't need to monitor it. And vacuum actually is possible by monitoring the decrease in terms of pressures that you have to keep it in order to have vacuum conditions. Of course, also there's no leakage in terms of the vacuum situations as well due to the damage of the tank. Okay, The fourth item to be compared is in turn whether these breakers here will give you the fire hazard or not. This is very obvious. Oil breakers can't escape for these situations here, but other breakers doesn't have such issue. Okay. The next one is in terms of health hazards rates here. So mostly is low, and air breakers here doesn't have the health hazards right now. The last one here is in terms of voltage applications range. So we know that for vacuums should up to medium voltage range or else is very costly for us to generate the vacuum condition. So you can see in terms of applications will be from 3.3 up to maximum is 36 kilowatts. So FSS gas here, right, it has an excellent properties, remember, so it can be applied to the highest system voltage we can apply. So from 3.3 up to 800 kilowatts. So for oil, right, it's not suitable for higher voltage application, so we only limit it up to 22 kilowatts. But for air breakers, seeing as it doesn't has using a high pressures and all, and the arcing emission is occurs at atmospheric pressure that you cannot control. So usually we only apply up to 1,000 watt system only. So this is compared in terms of this 1, 2, 3, 4, 5, 6 items here at the left hand side. So we have one more tables here as well, where also showing the comparisons of these four, one, two, three, four different kinds of breakers we have. So first one here is in terms of safety for the usage. So this is actually linked with this, the fire hazards, of course. All right, so the oil breakers here have the risk of explosions. All right, if let's say we have applied in a wrong manners. And how about air breakers here? As being mentioned just now, right? If you stand it's nearby it, there is an emissions of hot air. So the ionized particle will actually discharge to the surroundings. That is the air breaker. So you might feel not comfortable if let's say you are beside the air breakers. And then for vacuum and FSS gas here, so there's no risk in terms of explosions. This is quite logic. So in terms of size comparison, the biggest one we have is the oil breakers, followed by the air breakers and vacuum, and FS6 gas here is have the smaller size. Okay, it has a compact design, well enclosed. And in terms of maintenance, we know oil need to be replaced regularly. And the air breakers here, seeing as the arcing process is very long, so the contacts for the where the arcing occurs, right, might need to replace in much more frequency. But then for vacuum and FSA gas here, what you need to do is just the minor lubricants for the control device. Okay. In terms of environmental factors, whether it will affect the operations of these different breakers here. So we know that for oil breakers and air breakers, right? So for the humidity or the dust from the atmosphere might actually pollute the oil breakers as well as the air breakers. Okay, so with such a case, it might affect the dielectric strength of this medium. So the arcing process might be different based on these situations, the dust or the humids from the environment. But for vacuum and FSS gas, right, we doesn't have this issue. Why? Because it's completely sealed. So the effect from the environment doesn't come in place. Okay. The last one here is in terms of ability to withstand the high fault currents. Well, so we know that the FSS gas and vacuum have the excellent performance to deal with the high currents. For oil breakers doesn't really, is actually below average. Air breakers have average performance. So this is comparing different kinds of breakers as being introduced to you so far. Okay, so now we have few more topics, two more topics. So we'll move into the switch gears. So for switch gear, right? So this is the pictures of switch gear. As you can see, the size is so big, occupying the entire rooms here. So this switchgear itself is actually formed with many protective devices together. Okay. So now, how actually is being made? As being mentioned last week, right? Switchgear is actually a very big system, but it's a diode that composed with many components together inside, including the fuse, the circuit breakers, of course, we have relay also, all right? And we have an isolated switch, actuators and all. All right, so it formed a very big system. So in terms of size, if you are comparing these three major projective devices, switchgear will be the biggest, and inside switchgear it contains the circuit breakers and relay will be the smaller size. Okay, so usually relay we know is a low rating device, so it can't take high voltage or high current value from the power line. Okay, so what would be the importance feature should have for a switchgear to be applied in the system? The first one here will be the complete reliability. So what happens here? To have a high reliability of the system, which means that you have high security with high dependency. So during the event, if there is a fault occurs anywhere within the system, these switchgears must able to only isolate the fault sections up from the remainder circuit. So how actually we can achieve this? So we must have absolute discriminations, which means that you're able to tell whether this is an internal fault or external fault, which part is actually under faulty condition, which part is healthy situations. All right, so else it will cause the fault stripping. So these two is actually interlinked to each other. So of course, any protective system, we want to have quick operations, right? Clear fault from the power system as soon as possible, no fire hazards or no damage to the system components, right? So this is unavoidable. So the next one here, the feature should have for the switchgear will be the availabilities for the manual controls. Let's say in the event if the electronics control fails, so the technicians can actually take over using the manual control to initiate the tripping operations. So that is the fault features should have for the switchgears. The last one here, basically, this switchgear must be able to connect with the instruments like the voltage transformers and current transformer. So with such a case, we can get the voltage and current readings from the power networks. So here are 5 different features should have for a switchgear. So for switchgear topics, it's very small. It's only up to this point here. And the remaining slide is just showing you the samples of the switchgear we have. Okay. So now let's move on to the last topic in chapter 2. Yeah, it's almost there. Okay. So what is the problem faced if we have circuit interruption? So which means that during the time the breakers operates, open up its contact, we want to interrupt the circuit, right? There might be some problems occurs causing these breakers unable to isolate the fault from the system. So now let's check out the first bullet point here. So with the fact that the power systems, right, is actually consists of appreciable amount, which means that high amounts of inductance and capacitance. Remember due to the line is actually distributes with the inductance and capacitance value. And for this inductance and capacitance, right, they're actually the energy storing device, right? I'm not sure you know about this or not. So for inductors, right, it will store energy in the form of magnetic fields. For the capacitors, right, it actually store energy in the form of electric field, which is the charge. So what happens if we have fault occurs, right? This energy stored due to the inductance and capacitance of the system can actually become considerable, which means that the energy stored is actually very large. So during the time, if we want to interrupt the fault currents by initiate the operations of the breakers, so for this stored energy, right, it will actually mostly dissipate within the circuit breakers operations. But we might have remainders right now, and these remainders will actually dissipate through the auxiliary surge within the power system, which is not desired. So with such a case, we have to design a circuit breaker that can able to dissipate this energy that's being stored here as much as possible. Okay, so now let's move on here. We'll use these two figures here to explain the problem faced right now. So what happens So let's say this is the transmissions line, and this transmissions line we have short circuit conditions occurs here. And this line, right, is actually fed by a generation source, right? This is a transformer. So up along the line, right, we are actually using circuit breakers as a protective device. So we can actually draw out the equivalent circuit for these situations here at the right hand side. So here we have a generation source with voltage value, let's say at E here. So this line, right, it will be distributed along with the length with the inductors and capacitors. So remember, inductors will form the series impedance of the line. Capacitor will connect in parallel connections across the loop or the generation source here, like let's say the voltage source here. So this is actually coming from the transmissions line. So do you still remember actually we have resistance value as well? But right now for easier analysis, we actually neglect the resistance in the system, seeing as its value usually will be very small. All right, so what happens if a fault occurs right now? So let's see the problem phase. So during the times if we have the operations of circuit breakers to isolate the fault from the line, right, it might have the rates of the rise of the restricting voltage much higher than the growth rates of the dielectric strength we use for the materials that between the contacts of the circuit breakers. Okay, so with such a case, the arc will restrict again. So to understand states, so let's go through the bullet point here. So with the fact that the line will have some inductance value forming a series connections with the source and the loop, as well as the capacitance here in parallel connections to these generators, as can be told by looking into this equation. This one and the previous slide is actually the same. Okay, so what happens if a fault occurs on the transmission line? So we have short circuit situations right now. So the current that feed from the generation source here have two paths to choose. So it can either go through the short circuit path or go through the capacitors here. So we know that currents like to choose the low resistance path, correct? As what we have learned in chapter 1. So which means that it will ignore this path where the capacitors locate. Instead, it will going through the short circuit path. So in other words, we can say that this capacitor has been shorted by this short circuit path right now. So with such a case, if we measure the voltage, right? So you notice that this voltage from the generation side will drop across the inductance 100%, seeing as this one has been shorted, right? We have a short circuit at this path here. So with such a case, whenever we have inductance from the transmission line, so we have an inductive networks right now, you will notice that we will have the lagging power factor. So what happens if you measure the fault current, which is a short circuit current, you will notice that it will lag behind voltage by 90 degrees. That is the behavior for the inductive networks. So what happens if these circuit breakers start to operate? So open up the contacts to isolate the short circuit path. So which means that it will form a first order circuit. I'm not sure you know what is first order circuit or not. Is the circuit that contain the inductors and capacitors. So we have a LC circuits right now. So with these situations, with this capacitor, it will actually form a parallel connections with these circuit breakers. All right, so now there will be a voltage drop across the capacitor, and since this path in parallel connections, the same voltage will occur across the circuit breakers as well. And that is what we call it as the restricting voltage. Do you still remember? During the moment we have opened the contacts of the breakers, all right, so when the current is reaching to the zero state, we will might have the restricting voltage. All right, so this restricting voltage, the high voltage rate due to these capacitors here, right, actually help this arc to restrict again. So which means that arc is unable to be eliminated due to these capacitors from the transmission line. All right, so to further understand this and how actually we can solve these problems here, so let's move to the next slide. So what happens, this is actually the same situations. The generation source here, the line here, we have inductors in series, capacitor in pairs. So this is where the circuit breaker is located. Okay. So down here we have a voltage current waveform. Okay. So this is the voltage waveform from these generators. This is the fault current. Let's say we measure this. All right. So during the moments, if there's a separations of the contacts, right? Once the current reaches zero state, we know that there will be a restriking voltage which is appear across the capacitor. Seeing as this path in parallel connections, the same voltage will appear here, all right, which is across the contacts of the circuit breakers, and this voltage help the arc to restrict the gains. So that's basically the problems we might face during the time if we want to isolate these faulty transmissions up, transmissions line up by using the circuit breakers. So what we can do to deal with this, to stop this arc to restrict again. So the solution can be found in the next slide here, which is by using the recurring theory. So you have to choose the medium used between the contactor with the rate of rise of the dielectric strength higher than the rates of rise of the restricting voltage. RRRV here is a rate of rise of the restricting voltage. Okay, which is actually the titles here. RRRV. Okay, so now what is this here? So what happens if you check out these two waveform? This is voltage with respect with time. So now this is the risings of the restricting voltage. This is the risings of the dielectric strength. So if you choose the materials between the contacts of the breakers with the growth of the dielectric strength lower than the rates of rise of the restricting voltage, which means that these particles will turn into ionized. All right. So with this case, we can say the arc is unable to be removed. So what happens if we reverse these two conditions here? So the growth rates of the dielectric strength for the material used is much higher than the risings of the restricting voltage that generate across the context of the breakers. So in such a case, this is always higher, which means that the medium will not turn into ionized particles. So the arc is able to be extinguished. So the trick here is using the right materials with higher growth rates of the dielectric strength as comparing to this, the rates of rise of the restricting voltage. Okay, so that is the first problem. Okay, so we have another problem faced as well during the circuit interruptions. All right, it will be the current chopping. Remember, we have talked about this in brief manner just now. So for this current chopping, it's a situations where it will happen where the currents before reaching to zero state naturally. Let's say you have opened up the contacts of the breakers. All right, so these situations usually occur for air-blast circuit breakers. The reasons why it's because we want to maintain the same extinguished power regardless of what is the magnitude of the fault currents that you want to isolate from the system. So now we have a deionization effect through the air blast. So whenever it blows a compressed air towards to the arc formations, right, the current will actually fall abruptly to zero before it's reached to zero state naturally. So to further explain this, let's look into the waveform. Okay. So now we have the current, AC current with respect with time. So once the context of the breakers has been opened, right, we are expecting the current will fall to zero, right? But before it's fall to zero here naturally, there is sudden drop to zero due to the air blast. Okay, so like this case here, this is the first current chop, right? So second, third, and fourth. So every time there's a drop of current to zero, it will cause the voltage increase. All right, so whenever this voltage increase and is much higher than the restricting voltage, which means that due to this current chopping here, the arc will restrict again. Okay, so now you can see whenever the current has been interrupted before reaching the 0 point, there will be high voltage developed across the contacts right now. in which this help to generate the arc again. So how actually we can stop this from happening for the airbag circuit breakers, right? So we will need to add a resistance in parallel connections with contacts of the breakers right now. With such a case, we can stop the current chopping situations. All right, so here would be the solutions. So with such, we are reaching the ends of chapter 2. So you can see, right? So last week we have talked about the protective relays, and we have 3 generations of relays has been introduced to you. The first one is the EM relay, where it will be operates based on the electromagnetic principle. So I will help you to do the recap again on this Wednesday for the protective relays. So if you're comparing the part 1 and part 2 of chapter 2, right? I can tell you that for part 2 and of chapter 2 is only on the principle. So you know what is going to happen if, let's say, the question is tested you on the part 2 of chapter 2 is everything about the working principle, what is the pro and cons, how does the arc is actually generate, what is the way to element arc. So this is the possible problem might be passed you for part 2 of chapter 2. Even for the switchgear as well, you know, only have one slide for this, the essential feature for the switchgear. So during the time it's being asked with the topics related to the switchgear, definitely is the feature should have for a switchgear as a protective device, right? So that is basically what you have learned in chapter 2. So do you have any questions for me? Hello? Are you still here? No questions, all right. So I will, don't worry, I will help you to do the revisions again on this Wednesday whenever we have tutorial class. So try out the questions we have for the first tutorial. Only one question. The second question here is actually relates to this part 1 of chapters 2. Okay. So if you have no question, that's it for the day. So see you on this Wednesday. All right. See you.